unknown parameter, but that parameter is fixed. Okay? So what does that mean? That means that when you collect your data, you assume that those data come from some distribution. And then this distribution has some parameter theta, and the true underlying distribution, this data must take some value, so it's fixed. Okay? So let's say your score for your midterm follows a normal distribution. The mean is 90. Okay? So this data will be 90, it's fixed. And then you use the data you collect to try to estimate this mu, right, or theta. So that's the maximum likelihood approach. The Bayesian approach basically takes a different route. Bayesian framework basically assumes that the unknown parameter theta is random, and it follows some distribution. So this is the biggest distinction between the two approaches. Maximum likelihood approach assumes that there's a fixed data that you want to estimate. And then the Bayesian approach says that, okay, the data is unknown and you need to estimate it, but I assume that my data is also random and it follows some distribution. Okay? So that's the main distinction. And then which one is more reasonable? It really depends on your question, right? So the likelihood function basically is defined as this. We have seen this before. And so when is the Bayesian approach reasonable? It's when you have some prior knowledge in the problem. So to incorporate that in the Bayesian framework, we need to define the prior distribution. So suppose that you have in your statistical model, x given data, you have a parameter theta. If you treat data as random, then the distribution that they are assigned to data before you observe the x, this is called the prior distribution. So throughout the class, we will use this notation, pi of data, as the joint density function, or as the density function of the prior distribution for theta. Okay? So whenever you have prior information, you use this pi of data rather than f. That's also the standard notation people use. So here's an example. Suppose that we assume that x1 dxn obtained from tossing a coin, where xi equals to 1 if you get a hit. So this is Bernoulli with probability p, right? Suppose that you have prior knowledge that this is a biased coin. So let's say before I toss the coin, I tell you this coin is biased towards hit, right? So p is larger than 0.5. And because you have this very reliable prior information, then you can actually incorporate this prior knowledge by making the prior distribution for p say to be uniform from 0.5 to 1. So this is one way of incorporating the prior knowledge. Does it make sense? So we have defined what is called prior distribution. We have defined the likelihood function, and now we need to talk about posterior distribution. So these three are the key concepts in the Bayesian framework. Okay? So the posterior distribution is basically you have a parameter theta and you observe x1 dxn. So you calculate the conditional distribution of theta given your data x1 until xn, and this is basically called the posterior distribution of theta. And we typically use this notation pi of theta given x to denote this posterior distribution. Okay? So in other words, you have three different types of distribution. You have the likelihood function, you have the prior distribution that are used to incorporate the prior knowledge, and then you have the posterior distribution that is calculated when after you observe your data x1 until xn. Is that clear enough? So these three key distribution and function. Okay. So how do you calculate the posterior distribution? You actually already know how to calculate it from the previous class. using the Bayes rule, right? Or calculating the conditional density function. So suppose that you observe x1 and xn. You need to calculate pi of theta given x. So what you need to do here is to take the joint density function of x and theta and divide by the marginal of x, right? So this is what you learned in your previous class. And if I expand this term, this will just be the product of all of your data. And essentially, this is the linear function right here. So this will be a linear function. So this can be interpreted as what the data tells you, right? Your linear function is basically controlled by the x1 until xn you observe. Remember, I talked about the shape of the linear function changes when depending on what x you observe. So this is essentially what the data tells you. And then this pi is your prior information, right? So you basically just multiply what the data tells you and along with your prior knowledge, right? This is how you calculate your posterior distribution, okay? And then this f of x is basically the marginal density, but this quantity right here can be quite difficult to calculate. Usually, if the distribution is complicated enough, then f of x does not have a closed form solution, right? But then if you look at pi theta given x, this is a function of theta. This is a function of x, because you integrate out the theta. So we actually don't really need to care too much about this when we actually solve our problems. Because all we care about is the posterior distribution of theta given x, and we can just throw the f of x away, and then try to recognize what kind of density we have by taking the product of this, and then come up with a constant so that this integrates to 1. Okay? So essentially, this is just a constant, right, as a function of theta. So it may seem very vague now, but when we do an example, you will see what I mean, okay? So just to recap, the entire framework is pretty simple. You have a linear function, you have a prior distribution. You multiply both of them to get your posterior distribution, right? So pi theta given x is proportional to theta. And it's equal to basically f of x given theta times pi of theta. Okay? So here's a summary for you guys. Suppose that you observe n observation, x1 and xn. You have a prior theta from pi of theta. This is where you think your theta is. Okay? So if you have no prior knowledge, is it a good idea to use the Bayesian approach? Probably not. You should probably use the maximum linear approach, because the maximum linear approach shows you evidence based on data where your data should be, right? But if you actually do have prior distribution, right, you do have some prior knowledge, then it's always useful to consider a Bayesian approach. Okay? And you calculate the posterior distribution or density by taking the product, and this is proportional to theta. Okay? The posterior density can be interpreted as this is where you think data is after seeing the data. So you initially have a guess where the data should be, right? But then after seeing the data, you change your distribution a little bit. You update your prior information into so-called posterior distribution. So basically, this is what you this is basically where you think data is based on the evidence of your data plus your prior knowledge. Okay? So that's the entire framework. So let's try to work out a problem by calculating the posterior distribution. So suppose that we are interested in the proportion of defective items, data, and this data is unknown, right? And then the prior distribution of data is, let's say, beta distribution, okay? So this beta and this beta distribution have two parameters, and we assume that these two parameters are known. So suppose that you observe x1 until xn, where xi is basically binary with probability theta. Calculate the posterior distribution of theta. Okay, so let's try to do it. So because it's binary, xi given theta is Bernoulli. Okay? And then theta is beta distribution with parameter alpha and beta. So note how I actually write my axes. Because I'm in the Bayesian framework, I need to emphasize that data can be random. So therefore, I write xi given data follows a Bernoulli distribution. Okay? When I'm not in the Bayesian framework, I don't write this way, right? In our previous class, I just write xi follows a Bernoulli with parameter theta. But because we are working in the Bayesian framework, okay, this is important. Under Bayesian setting, data can be random, so I need to condition on my data so that xi given data follow the Bernoulli distribution. Okay? So I have these two, and then alpha and beta are known. So my fn of x given theta, I just write down the Bernoulli density, multiply them together. This is what I get. And then my prior density, because this is beta distribution, this is the form of the density function. And note that you don't have to memorize the density for beta throughout the class. If you need it, I will give it to you. Okay? So this is the prior density, the likelihood function. The posterior density, pi of theta given x, is proportional to theta. And because it's proportional to theta, this term right here, does it depend on theta? Probably not, so I can throw it away, right? And then I just need to keep terms that are related to theta, okay? So I have theta alpha plus sum of xi minus 1 minus theta, beta plus n minus sum of xi minus 1. Okay? So now, what is the posterior distribution of theta? Just looking at this density function, do you know the distribution? Is it similar to one of these?
Yes.
Right, so what is this distribution? It's beta, right? So that's why we can throw away the fn of x. Because essentially it's just going to appear in front of this so that this density integrates to 1. Okay? So that's why we can just throw it away. And we can just say that theta given x is beta distribution with alpha plus sum of xi, beta plus n minus xi. Okay? So this is how you would work on the kind of Bayesian problem for calculating the posterior distribution. And then the second example. Second example basically say that you have parameter theta and you model it using Poisson distribution. Okay? And then the boss of common coffee is actually a guy, so I should write he. So he assigns theta a gamma prior distribution with parameter alpha and beta. And again, alpha and beta here is known, okay, unknown. These two are known. So x1 to xn is basically a Poisson distribution with parameter theta. And then you have a gamma prior distribution on theta. What is the posterior? So you just do the same thing, right? So essentially, you just write down the density and first write down the distribution, right? Just to remind yourself. And then theta follows the gamma. And now you only need to write down the density. Fmx given theta. Just take the product of everything. And then you have pi of theta. I'm just writing down the density of a gamma distribution. And then I just need to multiply the two. And I can drop terms that are not related to theta. So I can drop this term. I can drop the x's, right? Because product of xi doesn't depend on theta, right? So I can just throw away this, and multiply terms that are related to theta together. So essentially, I get e to the negative n plus theta, and then theta alpha plus sum of xi minus 1. Okay? And so what is the posterior distribution of theta? So you again check, right? You check whether this is similar to, which one is similar to, right? It's similar to the gamma density, right? So therefore, theta given x is gamma with some parameters, okay? So you have this now. Any questions so far for the entire framework? Yep.
Actually, I'm a little confused about what does it mean to say that arriving the first hour becomes 10th hour.
Don't confuse about the text. That's not very important. I just basically come up with some fun story, that's it. Okay? So the important thing is that xi given theta is Poisson. So if you are confused about the text, that basically means that I didn't write it carefully. Okay? So all the framework is good? Okay, so now I have a question for you guys, okay? So for the two problems, I assume that the parameters in my prior distribution, I assume that they are known, right? For the two problems. So this is alpha and beta are known in example 1, alpha and beta are known in example 2, right? So what if they are known? What do you think people do if alpha and beta are unknown under the Bayesian framework? Any idea? Yeah, you just do a similar thing, right? You just say, okay, alpha follows another prior, beta follow another prior, okay? And then what will the process be? The process would be that this guy, xi given theta, depending on beta, right? Then you will write theta given alpha beta, right? So you write something like xi given theta, and then theta given alpha beta, and then you have alpha and beta. You have the density for alpha and beta, right? And then how do you calculate the posterior distribution of theta? You would basically multiply 4 of this density together, and then try to extract this as a function of theta, and then try to recognize how your posterior distribution look like. So this is called hierarchical Bayesian modeling, and we are not going to talk about this in this class, okay? So in this class, all we care about is that you have a xi given theta, and then you have a prior of beta, that's it, okay? So if you're interested in learning more about this Bayesian framework, Bayesian is actually used a lot in real application as well. So if you're interested, I think our department has 551 that you can take to learn more about this Bayesian kind about this. We are not going to cover this in this class. Okay, so the next example that I want to go through with you guys is sampling from a normal distribution. So in this example, x1, dxn are normal. And then your theta is the mean, this is unknown. And then to make the problem simple, we are just going to assume that sigma square is known, okay? Suppose that the prior distribution of theta is also normal. What is the posterior distribution of theta? Okay, so this is actually used a lot, and I think if you call yourself a statistician in the future, you must do this problem once in your lifetime, because this is very complicated. Okay, I think I actually assigned it as one of the homework problems to do it the usual way. I'm going to show you a trick to do it easily, but to do it the usual way is actually you need to do a lot of algebra. Okay. But you guys need to do it once. So let's write down the problem. So this sigma square is known, okay? And then theta follows normal with mu 0 and v 0 squared. And then these are known. So pi of theta, you just write down the normal density. And then fn x given theta, you also write down the density. And then the posterior is basically proportional to the 2. So I'm going to sort of derive this a little bit, and then in the very tedious step, I'm just directly going to tell you the answer. And then I think in one of the homework problems, you are supposed to show that step. Okay? So basically, I need to take the product of this and this and write it in terms of theta, right? And you can already see that there's an exponent term here. The denominator is different, right? One of them is sigma squared, one of them is v0 squared. How can you combine the two so that you can write as theta minus something? Okay? So this involves completing the square, right? So there's a lot of algebra here, but first I'm going to use the fact so that my form is a little bit nicer to work with. So I'm going to use this fact right here. Sum of xi minus x bar times x bar minus theta, this is 0. And the reason this is 0 because you can actually pull this x bar minus theta outside the sum, right? Because this x bar doesn't depend on I anymore, so you can pull it outside. And then sum of xi minus x bar is basically 0, okay? So x bar minus theta, sum of xi minus x bar is 0, since sum of xi minus and x bar is 0, right? So this is the first fact. The second fact is the following. I just add an x bar minus an x bar, and then I'm going to expand things out. And the cross term is basically just 0 because this is what we show, right? So there's a cross term here, sum of xi minus x bar times x bar minus theta, which is this term. And because we already say that this is 0, so the cross term can be removed. Okay? So therefore, I can rewrite my posterior as a function of theta, and I can take the product. So 1 over square root 2 pi, 1 over v0 doesn't depend on theta, I can throw it away. same thing here, I can throw this term away, right? All I need to keep is the term in the exponent term. So now I'm going to change this sum of xi minus theta to be the two terms right here. Okay? But then sum of xi minus x bar squared doesn't depend on theta. So I can throw it away. Okay? So all I have left is basically, I'm just going to write exp here so that it's easier to read. So I'm just trying to change this term to this term, and then I'm going to throw this away because it's no longer dependent on theta. So 1 over 2 sigma squared, and then I have n x bar minus theta squared, right? And then I have another term from the prior. And I'm going to call this equation 1. Okay? So now you need to merge these two together. This is theta minus x bar squared. This is theta minus mu 0 squared, right? So you need to find a way to combine these two together and write it as theta minus something squared so that you can say that the posterior is normal. Okay? So that's what you need to do. And then there's a lot of calculation here. We are not going to go through in this class, but you can just do it in one of the homework problem. I think I assigned it as one of the homework problem. So basically, the final answer is that you will be able to show the following. So this is v1 squared now, and then this is mu1 squared. So therefore, theta given x is normal mu1 and v1 squared, where mu1 is actually something complicated that takes this form. And then v1 okay? So you can already see that how much algebra you need to do to come up with this mu1 and v1, right? Have you guys done this before? In the previous class where you calculate the conditional density of normal? Have you done it before or no? No? Okay. So it's a good chance for you to practice. Everybody needs to do it once, okay? So yeah, you can see that normal is a very common distribution, but sometimes the density function is very hard to work with. Especially in the Bayesian setting where you have to be really good in algebra, completing the square and stuff like that to come up with a solution. The Bayesian framework also works in the multivariate setting when you have multivariate normal distribution, for instance, right? But instead of working with scalar here, you will be working with matrices. Okay? So I will leave this at here, and then I will tell you guys a trick on how to solve this problem in a more easy way. But before I do that, let me ask you a question. What if I change the problem a little bit? Okay? So I could have easily given an exam problem where I actually modify this a little bit, right? For instance, what could I do? I could say, okay, theta is now known, but sigma squared is unknown, right? So what do I do now? I would impose a prior distribution on sigma squared. And then I would do the same calculation to come up with posterior distribution of sigma squared given x. And then I say, okay, sigma squared given x follow whatever distribution that it follows, okay? So you can see that I can actually change the parameter, but then the idea is the same, right? The idea of the Bayesian approach is basically the same. Or to make the problem even harder, I could also change the parameter and say, okay, both mean theta and sigma squared are unknown, right? how would you solve this problem? You would still solve it the same way. Make sense? So in summary, when we have a Bayesian problem, regardless of how the parameter changes, the idea is basically the same. This is sort of like an algorithm, right? You write down the linear function, write down the prior density, and then you merge them together to come up with a posterior density. Okay? Yep?
So if we have two parameters, the prior knowledge of high data is like a joint density function.
Yes. So if you have, let's say, theta and sigma square are unknown, then you would have two prior distributions, one on sigma square, one on theta. Or you could have a joint density for theta and sigma square, okay? But then the framework is the same. Essentially, you just multiply everything together, try to come up with theta given x. Any question? Okay. So now let me talk about a trick that I learned long time ago that works with normal distribution, okay? So we can avoid calculating all this mess and still arrive at the same result. So here's the second approach. So I have xi given theta to be normal. This is from my problem. And then I know that x bar given theta is also normal with this variance. And then my theta is normal with mean mu 0 and variance v0 squared. Okay? So now, because theta and x bar are both normal, when I multiply them up together, the joint density, I can verify that it's also normal. Okay? So x bar theta is bivariate normal. And therefore, I can write in this form. So this is the mean, and then this is the variance. Okay? So once you have the bivariate normal form, we know that, I think from your previous class, we know that the conditional distribution of bivariate normal is also normal. And there's a formula for the mean and variance. And we can directly use that result, okay? So just to remind you, okay, maybe I will first calculate what these parameters are, and then I can use the conditional distribution formula, okay? So you have this information right here. These are all information from the problem. I didn't do anything special, right? So now I need to figure out what are these values. So the expected value of x bar. Can anyone tell me what is the expected value of x bar? Anyone? Yeah, so you have to be a little careful, right? So remember, I told you guys that in this type of Bayesian framework, you need to write condition on theta in your x's. Okay? So the expected value of x bar is not theta, because theta is supposed to be random. So you have to use law of iterator expectation, right? So this is the expected value of x bar given theta, and then basically I need to plug in this value. This value is theta, and then the expected value of theta is mu 0, right? So I have to be a little bit more careful with the Bayesian framework. And then the expected value of theta is just 0, so we have it's just mu 0, so we have mu 0 here, mu 0 here. right? So now we need to calculate the variance and the covariance. So the variance of x bar is basically, again, you need to be a little bit careful. You need to calculate the, I don't remember the name for this. What is the name for this formula? Do you guys remember? Law of total variance. So you need to use law of total variance, right? Because you have information on x bar given data. You do not have information on x bar, right? So then now you should plug in your x bar given data information. And this is basically V0 squared plus sigma squared over n. And then you do it for the same covariance of x bar and data. Again, you don't have information about x bar, but you have covariance, but you have information about x bar given data. So you need to use the formula like that. Right? And if you do not know why this is equal to this, basically you just write down the definition of covariance and then use law of iterator expectation inside, and you'll find that this equation is true. Okay? And then we already have the variance of data right here. So essentially, I have everything I need. So x bar and data follows normal with mu 0, mu 0. And then V0 squared plus sigma squared over n, V0 squared, V0 squared, V0 squared. Okay? So this approach basically only requires you to calculate the expected value, calculate the covariance and variance. So now you have the proper bivariate normal distribution. We are just going to use the formula of bivariate of the conditional normal distribution. Okay. So I need to calculate data given x bar. So I'm just going to use the existing result on the bivariate normal distribution to calculate my conditional distribution. And the result basically tell me data given x bar is normal with mu data given x bar and sigma squared data given x bar, and this is how my mu should look like. Okay, so basically I'm just writing down the formula for the bivariate normal, the conditional density or conditional distribution of bivariate normal, and then this mu theta given x bar is mu theta. Mu theta in our case is mu 0, right? So you have to plug it in. Okay, this rho is basically the correlation coefficient, and it's basically the covariance of x bar theta, standard deviation of x bar, standard deviation of theta. You need to find this value and plug it in, right? And then this same thing here, sigma squared theta is just V0 squared. You need to plug it in, okay? And once you plug it in, you will be able to show that this is your solution, okay? So which approach do you guys like better? Do you guys like this one better or the regular approach better? Any preference? Or both of them are terrible? Personally, I would like this approach better. Maybe you appreciate this approach better. after you work on your homework problem. Any questions so far for the normal distribution? If not, we'll keep moving on. Yep. This one? Yeah, so if you do not know how to go from here to here, write down the definition of covariance x bar and theta. So you would have the expected value of x bar theta minus the expected value of x bar times expected value of theta, right? And then you apply law of iterated expectation inside. Then you realize that, oh, you can change this term to this one and they are still the same. Okay? Any other question? Yeah?
Is that like E or C on the bottom, is that sample correlation?
This one?
Yeah.
Yeah, no, this one is the population correlation.
Population correlation.
Yeah. We are not talking about sample correlation, or these are all parameters, right? Any other questions? If not, we will move on. Okay, so let me know after a few weeks whether you appreciate this or the other one better. Okay. And then this one I'll leave it to you guys to practice. Essentially, it's the same thing. You have x from exponential distribution. The prior is from gamma, and the posterior should be from gamma. Okay. So just try it out and see what you get. Your midterm, we have one question from the Bayesian setting. Okay, I already tell you what I'm going to ask. So you need to know how to do this. Okay? Okay, so I'm not sure whether you guys realize, but if the prior distribution is chosen from a family of distribution and the posterior is also from that level of distribution, then we say that this is the conjugate prior. It's just a definition. So for instance, in the first problem, theta is from beta distribution, and theta given x is also from beta, right? So then theta is called a conjugate prior distribution. And then same with this one, theta is from gamma, posterior is gamma, so it's conjugate. So all our example here, we work with conjugate prior. Just because it's easier to work with and it has a closed form solution. Okay? In practice, many Bayesian approach that people take does not have a conjugate prior. They use a different form of prior that are based on their prior knowledge. And in that case, you will not have a simple form of theta given x. Theta given x is usually a complicated distribution or complicated density, okay, in practice. And then people will develop a lot of computing tools to try to sample from theta given x to calculate what are their parameters. For instance, I'm not sure if you've heard of MCMC, Markov Chain Monte Carlo, Metropolis Hasting algorithm. A lot of them are used to try to sample from theta given x. Okay? So if you're interested in this topic, 551 is a good course to take. Okay, so now we know how to calculate the posterior distribution. And then, so what's next, right? We calculate our posterior distribution. Can we say something about theta? What is next? So we are going to study what is called the Bayes estimator, okay? So remember our goal. Our goal is that we have a bunch of x's, x1 until xn, and we want to say something about theta, right? And we talk about multiple approaches to do that, MLE, methods of moments, and now the Bayesian approach. So we really need an estimate of theta. So having just the posterior distribution doesn't answer our question yet, right? We need to come up with an estimator. And under Bayesian setting, it's called Bayes estimator. So here is how we, in the following, we will try to discuss the Bayes estimator. So the Bayes estimator, before we talk about that, we need to talk about loss function, okay? So a loss function is basically denoted as L of theta and A. Theta is your parameter and A is just some real number. The interpretation is that you lose L of theta A if the parameter equals to theta and the estimate is equals to A. Okay? So basically it just measures the discrepancy between theta and A. So a good loss function should be 0 if A is equal to theta. That means that there's no difference in A, right? So this is the use of loss function. We also need to define a few other things. The expected loss function is just the expected value of our loss function, right? You just take the integral of L theta at A multiplied by the prior. Okay? So remember, pi of theta is your prior of theta. You want to estimate theta, but what if you don't observe x? How do you estimate theta? So and then how do you measure how well you estimate theta? You calculate the expected loss, okay? So now, because we're in the Bayesian framework, we have a bunch of x's. We use our posterior density, right? Instead of calculating the expected loss using the prior density, we can calculate the expected loss given our data using the posterior density. And it's the same deal, right? We just multiply our L with our posterior and integrate the theta out. That's our expected loss condition on data, okay? So now finally we can define what is our Bayes estimator. So again, you must have a loss function, okay? So under the Bayesian setting, when we talk about Bayes estimator, we have to involve a loss function. If you don't have a loss function, you cannot define a Bayes estimator. Is that clear? If your loss function is different, let's say you have two different loss functions, the Bayes estimator can also be different, even though their conditional distribution are the same. Okay? So let L be a loss function. Let delta star x be a value of A such that the expected loss function given x is minimized. So I want to find A so that this expected loss function is minimized, condition on my data. So if you can find such a delta star that minimizes the expected loss condition on the data, then that delta star is called the Bayes estimator of data. Okay? So basically, delta star x is chosen such that the expected loss given x is minimized. Does that make sense? So that's why the Bayes estimator delta star has to depend on loss. Depending on the loss, because you're essentially minimizing the loss, right? So depending on the loss, your delta star will be different, okay? You don't have to worry about it too much in this class, but if you take a more advanced statistical inference class or the Bayesian class, then you do have to worry about loss function. In this class, we are going to assume that the loss function is square error loss. So that is easy, okay? So Bayes estimator under the square error loss, let L of theta A be theta minus A squared. Let theta be a real value parameter, and suppose that posterior mean is finite, which is usually the case. You don't have to worry too much about the condition in this class. The Bayes estimator is basically the expected value of theta given x. Very simple, right? So how do you prove this? It's not that difficult to prove. You just need to write down the expected value of the loss. This is essentially theta minus A squared, and then pi theta given x d theta. And then basically I just expand this term out. and then I can write in terms of expectation. Agree? So now you want to find an A such that this quantity is minimized. How would you do that? You just take the derivative with respect to A, right? And set it equals to 0. So dA is basically negative 2 the expected value of theta given x plus 2A, and I want to set it equal to 0. And this implies that A is equal to the expected value of theta given x. Pretty simple, right? So, therefore, under the square error loss, when you are asked to find a base estimator, it's just the expected value of theta given x, that's it. Okay? So now what if I change the loss a little bit? Let's say if I want to consider the absolute value of theta minus A, rather than the square error loss, I want to consider the absolute value of theta minus A. Then the base estimator of theta would no longer be the expected value of theta given x. It will instead be the posterior median. Okay? So how to show this? Show it in the similar form, right? Right now the loss function, change this to absolute value of theta minus A, and then go through the same argument, find out what A minimizes this expected value. And it turns out that it will be the median, okay? But for the purpose of this class, we are not going to talk about this. We are going to focus on the square error loss. So the base estimator is just the conditional mean. Sounds good? Okay. So same with the MLE, the base estimator also have very nice property. So basically, if I'm interested in the function of my parameter g of theta, call it psi. So g of theta is basically a function of theta, and I call it psi. And suppose that I want to calculate my base estimator of psi under the square error loss. Then the base estimator for psi is just the expected value of psi given x. Okay? So one example is the following. Let's say psi is equal to 1 over theta. Then the base estimator for 1 over theta is basically just the expected value of 1 over theta given x. Make sense? So this is one of the property that base estimator has. So similar to the MLE, right? MLE we also have similar properties. If mu hat is MLE of mu, G mu hat is the MLE of G of mu. Remember that? So this is essentially very similar to that. Okay? Okay, so let's try to calculate our base estimator for some of these. So for the first one, the base estimator is basically just the expected value of theta given x, right? And in this case, it's just beta distribution. Theta given x is beta distribution. So you only need to calculate the expected value of beta distribution and call it a day, right? So the expected value of theta given x is alpha divided by alpha plus beta. And our alpha is basically alpha plus sum of xi. And then you sum the two parameters up, you get this, right? So this would be our base estimator. Okay? So now, let's try to study this quantity a little bit more carefully. So I'm going to rewrite this base estimator as the summation of two terms. Okay? So this is equal to alpha plus beta divided by alpha plus beta plus n times this. And then then I have the second term. Okay, so what did I do here? I basically just try to separate this into two terms, right? So I multiply alpha plus beta at the top. I need to divide alpha plus beta at the bottom. And then this is basically my first term right here, alpha term here. And then this is basically my second term here, sum of excited. Okay? So why do I want to do this? This actually tells a very nice story. So alpha plus beta divided by alpha plus beta plus n is something between 0 and 1. Agree? So this, you can interpret it as some weights, right? What is this quantity right here? Does anyone know what this quantity is? Yeah, the mean of our prior, right? So our prior of beta is beta alpha beta. So this is basically the mean of the prior. So this is the mean of the prior. And then this is 1 minus W times X bar. Right? So what does this tell us? This basically tells us that the base estimator is a weighted average of the mean of your prior information plus the mean of what your data tells you, right? So this X bar right here is also the MLE for data hat, if you remember, right? So this is what the data tell you. This is what your prior knowledge is, okay? So don't you guys think this is kind of nice? So it's kind of like a weighted combination of your prior knowledge and what your data tells you. So now, look at this quantity again. What if I have a lot of data points, right? If I have 1 million data points, do you trust the MLE better and better if you have 1 million data points? You do, right? So look at this, right? This weights is alpha plus beta divided by alpha plus beta plus n. When n actually increases, what happens to this quantity? The W is actually getting smaller and smaller, right? And 1 minus W is going to 1 because W is going to 0. So what does this tell you? This basically tells you that as you observe more and more data, the base estimator weights more and more heavily to your data. It's kind of nice, isn't that? What if you only have n equals to 2? Right? If I only observe 2 data points, can you say something using the MLE? You probably shouldn't, right? Because how can you use 2 data points to infer 1 parameter? It's not going to be very accurate. So when n is very small, base approach usually is more preferred because you can incorporate prior knowledge, and your weights for the prior knowledge is going to be very heavy, right? So if you really have strong prior knowledge and your n is not very big, then personally I would recommend using the Bayesian approach in solving your problem. Okay? Does that make sense? Great. Yep.
So the unit or dimension matters because only even if n equals 2, but like our alpha equals 0.1 and beta like 0.1, the omegas will still be really small.
Oh, so his question was that what if my alpha and beta are very small, right? My W or omega will still be very small. So if my alpha plus, but then, I mean that's a valid concern. If your alpha and beta is very small, that probably means that you're not very confident about your prior, right? Your prior knowledge is not very confident. You don't have a lot of confidence in your prior knowledge, right? So that's fine, right? So you can think of beta is harder to think about, but if you think about this as a normal case, right? And let's say your variance is super big, right? Meaning that you have less confidence here. And when you do that, when you have a super big variance, your W, you can try at home, right? Your W will be also very small because you're not confident. Okay? So this is one of the advantages of Bayesian approach is that you can separate the terms and try to provide more interpretation. And if you think about it, it actually makes a lot of sense, right? This approach, as you get more and more data, the prior knowledge doesn't really matter anymore. Okay? So in the Bayesian setting, so I'm not a hardcore Bayesian or hardcore MLE person, right? But some people are, right? If they follow their Bayesian perspective, they always want to stick with Bayesian approach, right? But what if they don't have prior knowledge? How do they solve this problem? So there's something called non-informative prior that people use, but we are not going to talk about it here either, okay? So everything that we are going to cover in this class would be a regular distribution, conjugate prior, something that is easy for you to work on, okay? And we have already talked about this. When n is large, prior doesn't matter too much because the weights go to 0 essentially. So the disadvantage of Bayesian approach is that you need to specify prior, right? But I may have a different prior than you. So whose prior is correct? But in this case, it doesn't really matter because when n is large, prior doesn't matter too much anyway, right? So, but then this also kind of bring it back to the counter Bayesian people because people that are not, hardcore Bayesian, they will say that okay, if it's not going to matter much at all, why do I use the Bayesian approach? I could just do the MLE, right? So my take on this is that if you have limited sample size and strong prior information, then maybe Bayesian is the way to go. Okay? Otherwise, when n goes to infinity, I personally prefer using the MLE or something else. So that's everything that I want to cover today, and we are going to talk more about unbiased estimator on Thursday.